So these are notes. These are notes again on chapter 28 to 29. It's the last new topic of the year. Chapter 28 is the electric potential. Chapter 29 is relating electric potential to electric field. So it covers all of chapter 28, the first four sections pardon me, of chapter 29. We've already done the rest of chapter 29, which is capacitors and relating the electric field and a capacitor. So we'll finish up this week, hopefully, with this new content. Next week, we'll do some AP reviews, and we'll also do a lab with a virtual lab, rather, with circuits, and I think that'll be, or with capacitors, I think that'll be useful. All right, there are going to be two code words in this particular list or screencast to help you make sure you pay attention. And I think they're going to be important. And if you do those, you'll get full credit for this particular sort of assignment. The first code word is Charlie. Charlie is the first code word, and we'll go from there. All right, so I'm going to upload a PDF of this as well so you can look at it. I'd encourage you to go through chapter 28, 29 a bit, but this is the condensed version, and it's still kind of lengthy. So the idea is electric potential is voltage. It's a tough concept because it's not energy, but it's energy per charge, or joules per coulomb. It's much easier, I think, to understand voltage in terms of how it pushes or current along in a circuit than it is in free space. So we're going to use some analogies to help us out with that. So from a point source, voltage is equal to KQ over R. Okay, so the question would, and it's the summation, if you have multiple charges of multiple KQ over R's. It is a scalar quantity, but it can be positive or negative. It does not have a direction, though. So why is that? Well, if we think about work as force times distance, or is basically the integral of the dot product of those things in calculus, and work is equivalent to energy. So if we think about this force as being like from a point source is K Q1 Q2 over R squared, and then we multiply that by the distance those things are from each other, we would get something over R instead of R squared. But I'm going to go through that, I think, a little bit down here, so I should just shut up about that at this point. So volts are joules per coulomb. Force times distance is work. So over charge, FD over Q is what a voltage is equivalent to. So here, again, if we look at this, we've got this force between two charges as up here, multiplied by that distance, that gets rid of one of those. The charge down here and the charge down here cancel out one of the charges. So basically what that says is that the electric potential is equal to, goes back again to this KQ over R. Now, we've already figured out that electric field strength from a point source is KQ over R squared. We'll talk about that in a little bit and how those relate to each other. Because basically how voltage is changing with respect to distance, how rapidly that's changing is another way to think about electric field strength. So if we notice something like that. Now the symbols on your formula sheet may be a little bit different than this. They use S's sometimes instead of X's. So again, voltage is equal to electric field strength multiplied by distance, or rearrange something like this. Change in voltage over change in position is equal to electric field strength. The negative here is basically because by convention, electric field points from positive to negative. So points from a higher potential to a lower potential. And so if you're talking about a change in something like this, negative of the change gives us the electric field strength. We've seen things like that before, where if we had a graph of something, it's the negative value of the slope that's really meaningful. And I think that was first semester we had that with a potential energy versus position graph. And the slope, negative the value of the slope was equal to the force. Okay, so in this particular case then, if we have electric potential up here, we want to find out the potential energy between two charges, we would multiply this potential by the second charge. So this V, which is what we've got over here, is also something that would go into this equation. So technically, we can have, it should be really Q equals delta V, so electric potential energy U is equal to Q times delta V. That's actually a pretty darn important and universal equation. I'll move that up here. Okay, so electric potential energy between charges depends on the potential caused by one charge interacting with another charge. In general, I guess that's what I had up here. Duh. So the potential energy difference is equal to this. So I'll get rid of that. In a uniform electric field, where voltage is equal to electric field strength times distance, which is again what we had over here, then the difference in potential energy is QE. So that's charge times electric field strength, which is force per charge, times distance. And again, notice that force times distance would equal energy. So a lot of these things kind of mathematical proofiness. So again, since electric field can be thought of as the rate of change of potential with respect to position, if we think this is generally electric potential and position is changing, that's how we end up getting that KQ over R squared. Okay. So we're going to do a gravitational and electric analogy. And now the second word of your code phrase is Hewland. So remember, the first word was Charlie. The second word of the phrase is Hewland. All right. So we have uniform gravitational fields. If you think of a near-Earth situation, where the gravitational field doesn't change by very much if you go up on top of a mountain or in a valley or things like that. It's basically a ratio of force to mass, gravitational force to mass. So it's newtons per kilogram. Here, if we have a uniform electric field, as often happens between the plates of a capacitor, we think of a force per charge, so newtons per coulomb. So here we can get the force by multiplying the mass times the field strength, gravitational field strength. Here we can get the force by multiplying the charge times the electric field strength. So there are forces between masses. This is Newton's universal law of gravitation. There are forces between point charges. This is Coulomb's law. Very similar, right? Gravitational potential energy can be thought of in a uniform field as something like this. mg, which is the force, multiplied by the amount of height that you've elevated. Here, if we think of electric potential energy in a uniform electric field, we think about it as charge multiplied by the change in potential. So essentially, this delta V times Q is equal to this mgh. M and Q are equivalent. G delta H is equivalent to delta V. Oh, I said that. If you have between masses in a non-uniform case, so this is potential energy where we do not have a uniform field, this is on our mechanics formula sheet. Why is it negative? Because masses are always attracting each other. And so when you have objects that attract each other, we have negative potential energy. And that's true of all bound systems, that they have negative mechanical energy. Again, the R here as opposed to R squared, and the fact that it's negative basically is due to the fact that if we take this up here and we take the derivative of this with respect to R, this is really R to the negative 2, then we get something like this. So if we end up having, this is potential energy between two masses, here's the potential energy between two charges. Again, looks very similar. Now, here, the key thing is yeah, opposite charges, so if this one of these is positive and one is negative, would result in negative potential energy since they would attract. That's similar to over here, gravitational potential energy. Two masses always attract, and they have negative potential energy. If we have two like charges, two positives or two negatives, this comes out to a positive value. Those charges would repel, and they would have positive potential energy. This term voltage or potential, electric potential, is a pain in the butt because there's so many things which sound like it. Potential, electric potential difference, voltage difference, delta V. These all mean the same thing, or very similar. Ooh, getting windy outside. All right. Electric potential can be thought of like elevation. So this is another way where I think the analogy with gravitation and electricity is going to be very useful. So if you're close to a positive charge, that's like being high in the mountains. You could think about being at a positive charge would be at the peak of an infinitely high mountain, and being close to a negative charge would be like being in a valley. And if you were trying to sit on that negative charge, it would be like a valley that's infinitely negative, below sea level. Zero voltage would be like being at sea level. So in some ways, I like to think about this like contour maps. And I'm going to show you, I think I've got those here from last year. So if we have something like this, this is actually from like earth science. So if we have these equal elevation things, those are called contour lines. In electricity, we could think of these as equipotential lines or lines with the same voltage. So this might be at plus 280 volts, plus 260 volts, plus 240 volts, plus 220 volts, plus 200 volts, and something like that. When these lines are close together and we have a steep slope, we have a rapid change in voltage over distance. That means we would have a strong electric field. Here, if we have a gradual slope, elevation-wise, that means it would be gentle, like in terms of like if you had a ball rolling down this hill, it would accelerate at a low rate. If you had a ball rolling down this hill, it would accelerate at a high rate. In terms of potential in electricity, here we would have a weaker electric field. So again, a charge would accelerate less in this area compared to in this area. Really good analogies. And because these are positive values, this indicates we're getting to a mountain peak. If these were positive voltages, this would indicate that we've got a region here with positive charges. Okay, so we've already seen electric field can be defined as this, force per charge, newtons per coulomb, but we can also think of this as in volts per meter. They seem different, but they're not. I think I've done this before in class, but if we think of a volt as a joule per coulomb, we see a volt per meter is equal to a joule per coulomb times meter. Okay, so voltage over distance, force over charge. Well, if a volt, again, is a joule per coulomb, actually, I don't think I've got that right. Volts per meter, joules per coulomb, but a joule is a force times distance over that. Okay, got it. So now we take this is over a coulomb times a meter, by the way. We cross multiply. We end up getting joules times coulombs, Newton meters times coulombs. Same thing. So electric field can be thought of as a rate of change of voltage with respect to position. That should sound like calculus. So electric field is like the steepness of a mountain or valley. I just talked about that a little bit earlier. And we saw this on the first page. So this joule per coulometer, by the way, that I was a little confused about came from looking at something like this, volts over distance. That's where that comes from. Okay, so now I've got some analogies I'm going to think about here. I may come back to these in a little bit. I want to maybe do those separate. So I want to do a comparison of position time graph with a voltage versus position graph. So here we have position versus time. If we have something with a constant slope, that represents the velocity. The slope of this graph, voltage over position, represents the electric field strength. If we look at a velocity versus time graph for this position graph, we have a positive velocity over time. The area represents displacement. And remember, the velocity would be the rate of change of this graph with respect to this. Now, the slope of the area of this graph represents potential difference. Why? Because the slope of this graph, voltage per meter, would be electric field. And so if we add electric field over position here, volts per meter times meters gives me volts, just like meters per second times seconds gives me meters. So this area represents the potential difference as you're going from one spot. Oh, goodness gracious. From one spot to another. Now, this is the tricky part. So in fact, from what I said before, which was back here, now I want to go back there again, the electric field points in a direction from a higher potential to a lower potential. So it's negative change in voltage with respect to change in position. So what that really means here is this graph here would be below zero. The slope of the graph of this graph would still tell me the absolute value of this electric field strength, but it would just be negative if this had a positive slope. Okay, so what does a constant slope mean for this graph? It means a constant velocity. What does a constant slope mean for this graph? A constant electric field. Steeper slope would be a higher velocity or a faster speed. Steeper slope here, stronger electric field. So what would a graph with a negative slope mean? Here it means it's a negative velocity. Here it means that you have an electric field pointing in an opposite direction of what you would if you had a positive slope. What about what a graph with a changing slope mean? Well, here it represents that the velocity is changing, that's acceleration. Here it means that the field strength is changing. So for example, in a point source, if we're looking at a point source, we would not have a nice uniform line like this. If we're getting close to the charge, we would exponentially curve up. If we're getting away from a charge, we would exponentially curve down in terms of the potential with respect to position. What would a graph with negative y values represent here? Well, all that means, if I have the same graph, but it's below zero position, it means that I'm a negative position. Here, all it means is I'm changing voltage from a negative voltage, which means I'm at or close to a negative charge. So I'm at a negative position. I happen to have a negative voltage, which just means I'm close to a negative charge. If I still have a positive slope here, but negative values, that means that the electric field is changing in the same way it was in this graph. It just means we're starting at a negative voltage. Final thoughts on this. Electric field lines that are closer together represent a stronger electric field. Electric field lines represent the direction of force on a small positive test charge at any location. Why small? Well, if it's a larger charge, it basically would in and of itself distort the field. So we think of a test charge as being something that wouldn't affect the field. When we think of uniform electric fields, say between plates of a capacitor, changing electric fields from a point source. Uniform gravitational fields close to the Earth's surface or planet surface, changing gravitational field when we look from a fairly far distance from the Earth's surface. Electric field inside a solid or hollow conductor, by the way, is electrostatic equilibrium is always zero. Otherwise, the charges wouldn't be at rest since they'd experience a force. And this also means that for a conducting surface, the electric field lines must always point perpendicular to the surface, because for a metal, this has to be an equipotential surface. If it wasn't equipotential, that means it does not have the same energy per charge. If some of these charges have more energy than others, that means they would instantly push or move on the other charges, and they would redistribute, and that would happen essentially instantaneously. So those are the things that are mentioned here. Notice that if I have a non-uniform shaped conductor, the charges can pile up at certain surfaces, so at the pointy surfaces, but they don't necessarily, or they don't have different electric potential. The reason they pile up here is because of how their fields point out at each other, outwards. So you can pile more up at that particular location. And I will actually end up doing this sample problem a little bit later. So I'm going to quit this one. The last code word for the phrase here is has been absent. So the total phrase, Charlie Hewland, has been absent. We miss him. So that's all I've got for that.